Albert Einstein once looked at quantum physics and felt something was deeply wrong. Not because the math failed, the math worked beautifully, but because the universe it described seemed almost impossible to believe. In the normal world, things are simple. A ball is here or there. A rock follows one path. A car turns left or right. A coin lands heads or tails. But in the quantum world, this common sense begins to collapse. An electron does not behave like a tiny ball. A photon does not behave like a normal wave. A particle can act as if it explored multiple paths at once. And the strangest part is this. The moment you try to watch which path it takes, the behavior changes. This is why the double-slit experiment may be the most disturbing experiment in all of science. Fire electrons through two tiny slits one at a time, and each electron arrives as a single dot. Click, one particle. Click, another particle. Click, another. But after thousands of electrons, a wave-like interference pattern appears on the screen, as if each electron somehow went through both slits, as if it interfered with itself, as if nature was refusing to choose a single path until measurement forced the issue. Then you place a detector near the slits to see where the electron really goes, and suddenly the interference disappears. The electron behaves like an ordinary particle again. Two paths become two simple patterns. No mystery, no wave stripes, no interference. So what changed? Not the electron gun, not the screen, not the slits. The information changed. When nature allows the path to remain unknowable, probabilities interfere like waves. When the path becomes knowable, the wave-like pattern vanishes. Einstein hated the idea that reality could depend on probability in such a deep way. He famously resisted the thought that nature was built on uncertainty. But experiment after experiment sided with quantum mechanics. And this is the terrifying lesson. At the smallest scales, nature does not work like the world you see. Particles do not simply have definite paths waiting for us to discover. Position and momentum cannot both be perfectly fixed. Atoms are stable because uncertainty protects them from collapse. Matter has structure because electrons obey strange quantum rules, and everything around you, the floor, your body, the light in your eyes, exists because the universe is quantum underneath. So the real question is not, why is quantum physics strange? The real question is, why does this strange quantum world create a normal-looking universe at all? To understand why quantum physics disturbed Einstein so much, we must begin with the world we think we know. In daily life, reality feels clear. A stone is in one place. A chair is in one room. A ball rolls along one path. A car cannot turn left and right at the same time. If something happens, we believe there is a definite story behind it. Even if we do not see the story, we assume the story exists. If a coin lands on the floor, we may not know whether it is heads or tails until we look. But we still believe it was already one of them before we checked. That is classical thinking. And for big objects, it works beautifully. Newton's world is a world of definite paths. If you know where something is, how fast it is moving, and what forces act on it, you can calculate its future. A planet follows an orbit. A falling apple follows a path. A cannonball flies through the air according to laws. This is the world Einstein inherited, and Einstein loved deep order. He believed nature should be understandable, not necessarily easy, but consistent. Behind every event, there should be a real physical reason. Then quantum mechanics arrived and broke that expectation. At the scale of atoms and particles, nature stopped behaving like a machine made of tiny balls. Electrons did not act like miniature planets orbiting a nucleus in a simple way. Light did not act only like a wave. Matter did not act only like particles. The smallest pieces of reality seemed to change their behavior depending on how they were tested. And the experiment that reveals this most clearly is the double-slit experiment. It begins simply. Imagine a wall with two narrow openings. Behind that wall is a screen. Now imagine firing tiny particles toward the wall. If you fired ordinary bullets, the result would be easy to understand. Some bullets go through the left slit, some go through the right slit. On the screen, you would see two main groups of impacts, one behind each slit. That is what common sense predicts. Now imagine water waves moving toward the two slits. The wave passes through both openings. On the other side, two waves spread out. Where the crest of one wave meets the crest of another, they strengthen each other. Where a crest meets a trough, they cancel. The result is an interference pattern, stripes, strong areas, weak areas, a wave signature. So far, everything makes sense. Bullets make two clumps. Waves make interference. Now do the experiment with electrons. This is where reality begins to feel impossible. Electrons are often described as particles. They arrive at the detector one at a time. Each arrival is a single event. Click. One electron, click. Another electron, click. Another. There are no half electrons, no quarter electrons, no blurred pieces arriving gently across the screen. Each detection happens as one complete particle-like hit. So naturally, you might say, the electron must have gone through one slit or the other. That sounds reasonable. If the electron arrives as one whole particle, surely it traveled as one whole particle. It must have chosen a path. But when both slits are open and electrons are fired one at a time, something astonishing happens. After many electrons build up on the screen, the pattern is not two simple clumps. It is an interference pattern. Stripes, like a wave, like water. But how can that be? If each electron travels alone, what is it interfering with? There is no second electron beside it. You can fire them slowly, with long pauses between each one, and the same pattern eventually appears. Each electron seems to arrive as a particle, but the probability of where it lands behaves like a wave. This is the first crack in common sense. Now let us test the obvious idea. Maybe each electron really goes through one slit or the other, and the interference pattern is just some hidden effect we do not understand. So close one slit, fire electrons. You get one pattern, a broad distribution behind the open slit. Now close that slit and open the other. Fire electrons again. You get a second distribution. If electrons are simply choosing one path or the other when both slits are open, then opening both slits should just add the two patterns together. Some electrons go left, some electrons go right. Two simple piles. But that is not what happens. With both slits open, some places on the screen receive more electrons than expected. Other places receive almost none. Opening an extra path can reduce the number of electrons arriving at certain points. That is not how bullets behave. That is how waves behave. So the electron is not behaving like a normal particle traveling through one unknown path. Its probability seems to depend on both slits being open, as if the electron's possible paths are interfering with each other. This is where Einstein would begin to feel the discomfort, because the mathematics works. It predicts the results with astonishing accuracy, but the picture behind the mathematics is deeply strange. Is the electron a particle? Yes, because it arrives as one complete detection. Is it a wave? Yes, because its probability creates interference. Is it both? Not in the ordinary everyday sense. It is something deeper, something that does not fit neatly into the categories our brains learned from rocks, water, and moving objects. Quantum physics does not say the electron is secretly a tiny ball with a hidden path we simply failed to observe. If that were true, the two-slit pattern would look like ordinary particle behavior, but it does not. The electron behaves as though all possible paths matter until a measurement forces a definite outcome. Now comes the next move, the move anyone would make. You say, fine, let us watch it. Place a detector near the slits. Make the experiment reveal which slit the electron goes through. If the electron passes the left slit, the detector records left. If it passes the right slit, the detector records right. Now we should finally know what is really happening. And when you run the experiment with the detector active, something remarkable happens. Each electron is detected at one slit or the other. Never half at one and half at the other, never both in an ordinary sense. So it looks like the mystery is solved. The electron did go through one slit. But then you look at the screen. The interference pattern is gone. The stripes disappear. Instead, you get the ordinary particle pattern, two broad groups, just like you would expect if electrons behaved like tiny bullets. The act of making the path knowable destroys the interference. This is the heart of the quantum mystery. When the path is not measured, the electron produces interference. When the path is measured, the interference disappears. So what changed? A careless explanation says, observation creates reality. But that is too vague. A better explanation is this. In quantum mechanics, distinguishability matters. If the experimental setup allows the path to be known, the alternatives no longer interfere in the same way. If the path cannot be known, the alternatives interfere. This is not about a human eye magically staring at the experiment. It is about whether information about the path exists in the physical setup. If the universe contains a record of which slit the electron used, the interference is lost. If no such record exists, the interference can remain. That is far more subtle than ordinary observation. Now imagine using light to see the electron. You shine light near the slits so that when an electron passes through, it scatters a photon. That flash tells you where it went. But light itself is quantum. It comes in packets called photons. If the light is strong enough, you get clear path information, and the interference vanishes. If the light is too weak, sometimes no photon scatters. In those cases, you have no path information. And when those no information events are separated out, interference returns. This tells us something profound. It is not merely that the electron was bumped or disturbed in a simple mechanical way. It is that the possibility of knowing the path changes the kind of pattern nature allows. Perfect path knowledge gives no interference. No path knowledge gives full interference. Partial knowledge gives partial interference. That relationship is not random, it is exact, and it leads to one of the deepest rules in quantum mechanics. You cannot demand every classical fact at once. You cannot insist that the electron has a definite path like a bullet and also keep the wave-like interference. Nature does not give both pictures at the same time. Einstein resisted this kind of reality. He wanted to believe that particles had definite properties whether or not we measured them. He believed there must be a deeper layer, a more complete description, something behind the probability. He did not like the idea that chance and uncertainty were fundamental, but the experiments kept agreeing with quantum mechanics. And this is what makes the double-slit experiment so powerful. It does not require a giant machine. It does not need a black hole. It does not need a galaxy. It reveals the deepest strangeness of reality with two slits and a screen. Particles arrive as individual events. Probabilities behave like waves. Measurement changes the available pattern. And the path the particle really took is not something quantum mechanics always allows us to ask in the old classical way. This is why quantum physics is not just difficult. It is a direct challenge to the way the human mind expects the world to work. We evolved in a world of tables, stones, animals, rivers, and planets. But atoms are not tiny versions of those things. Electrons are not little planets. Photons are not little bullets. The quantum world has its own rules, and those rules are not optional. They are the reason matter exists. They are the reason atoms do not collapse. They are the reason light is emitted in specific colors. They are the reason chemistry works. They are the reason the solid floor beneath you feels solid. So the double-slit experiment is only the beginning. Because once you accept that nature does not allow perfect path knowledge and full interference at the same time, you arrive at an even deeper rule. A rule Einstein could not ignore. A rule that says there are limits not only to what we know, but to what can be definite in nature. That rule is the uncertainty principle. The uncertainty principle is often explained badly. People say it means our instruments are not good enough. They say if we had a better microscope, a better detector, or a more delicate machine, we could finally know exactly where a particle is and exactly how fast it is moving. But that is not what quantum physics says. The uncertainty principle is not a weakness of measurement. It is a feature of nature. At the quantum level, position and momentum are not two perfect hidden facts waiting for us to uncover. The more sharply one is defined, the less sharply the other can be defined. This sounds absurd in everyday life. A car has a position and a speed. A cricket ball has a position and a speed. A planet has a position and a speed. But quantum objects are not tiny versions of cars, balls, or planets. They are described by waves of probability, and waves have a strange property. A wave with a very definite wavelength spreads out. It is not squeezed into one tiny point. Because its wavelength is well defined, its momentum is also well defined, but its position is uncertain. Now make the wave packet shorter. Squeeze it into a smaller region. Now you have a better idea of where the particle may be. But to create that short wave packet, you must combine many wavelengths together. Many wavelengths mean many possible momenta. So the position becomes clearer, but the momentum becomes less certain. This is not because someone disturbed the particle. It is because wave-like things cannot be both perfectly localized and perfectly wavelength defined at the same time. That is the heart of uncertainty. And once you understand this, one of the greatest mysteries becomes clearer. Why do atoms exist at all? Think about the atom. A tiny positive nucleus sits at the center. Negative electrons are associated with it. Opposite charges attract. So a simple classical question appears. Why do electrons not just fall into the nucleus? If an electron were like a tiny planet orbiting the nucleus, classical physics would predict trouble. A charged particle moving in a curved path should radiate energy. It should lose energy, spiral inward, and collapse into the nucleus. If classical physics were the full story, atoms would not be stable. Matter would not exist as we know it. The floor beneath you would not hold. Your body would not hold. Stars, planets, water, chemistry, life, none of it would have the structure we see. So what saves the atom? Quantum mechanics. The uncertainty principle prevents the electron from being squeezed into the nucleus. If the electron were confined to an extremely tiny space, its position would become very certain. But then its momentum uncertainty would become enormous. That would mean enormous kinetic energy. The atom finds a balance. The electron is not sitting on the nucleus, but it is also not flying away freely. It occupies a quantum state, a spread-out probability pattern around the nucleus. This is why atoms have size. Not because electrons are little balls orbiting like planets, but because quantum uncertainty creates a stable structure. Einstein may have disliked the philosophical meaning of quantum probability, but even he could not ignore the power of the theory. It explained why atoms are stable. It explained why matter has structure. It explained why electrons can only occupy certain energy levels. And that brings us to another strange rule. Atoms cannot have just any energy. They have specific allowed energies. This is not how everyday objects behave. A ball can roll at almost any speed. A car can move at 20, 21, or 21.5 kilometers per hour. Classical systems often allow continuous values, but quantum systems are different. An electron bound in an atom behaves like a confined wave. And confined waves have special allowed patterns. Think of a guitar string. It cannot vibrate just any way it wants. It has natural modes. Certain patterns fit, others do not. Think of sound inside an organ pipe. Only certain resonant frequencies fit the length of the pipe. In the same way, electron waves in atoms can only fit in certain allowed ways. Those allowed wave patterns correspond to allowed energies. The lowest energy is called the ground state. Higher allowed energies are excited states. When an atom absorbs energy, an electron can jump to a higher state. When it falls back down, the atom emits light, but it does not emit any random color. It emits a photon with energy equal to the difference between those levels. That is why atoms produce specific spectral lines. Hydrogen gives one set of colors, neon gives another, sodium gives another. Every element has a quantum fingerprint. This is how scientists can look at light from distant stars and know what those stars are made of. A star may be hundreds or thousands of light years away, but its light carries the signature of atoms. Quantum mechanics lets us read that signature. So the strange rules of electrons are not just laboratory curiosities. They are how we understand the universe. They explain why the sun shines, why atoms emit light, why chemistry works, why your phone screen glows, why lasers exist, why modern electronics exist, why the world is solid. Now let us return to the floor beneath you. You feel it as solid, you trust it. You stand on it without falling through. But why do you not fall through it? At first you might say because atoms are hard, but atoms are mostly empty space. If the nucleus were the size of a small bead, the electron region would be enormous compared with it. Matter is not solid in the simple way our senses imagine. So why does the floor resist your body? Part of the answer comes from electromagnetic forces, but quantum mechanics gives the deeper structure. Electrons cannot all be squeezed into the same state. They obey rules that prevent matter from collapsing into a featureless lump. The uncertainty principle and the Pauli exclusion principle help create the resistance that gives matter its shape and stability. When atoms are pushed too close together, their electron wave patterns are forced into smaller regions. That raises their energy. The system resists compression, so the solidity of the world is not simple contact between tiny hard balls. It is quantum structure. You do not fall through the floor because the electrons in your body and the electrons in the floor cannot simply ignore quantum rules. What feels like ordinary solidity is actually the result of invisible quantum laws operating everywhere. This is the strange miracle. The world looks classical because quantum rules organize it from below. Now, the double-slit experiment taught us that when alternatives cannot be distinguished, amplitudes interfere. This is one of the core rules of quantum mechanics. If there are two possible ways for an event to happen, and nature does not leave a record of which way occurred, we do not add ordinary probabilities. We add amplitudes. Amplitudes can reinforce, they can cancel, they can create interference. But if the paths become distinguishable, even in principle, then interference disappears. We add probabilities instead. That one rule explains the double-slit experiment, but it also explains far more. It explains how identical particles behave. Imagine two electrons scattering from each other. After the collision, one electron goes one way and one goes another way. But electrons are truly identical. There is no label written on them. You cannot say, this is electron A, and this is electron B in the ordinary way. There are multiple possible histories leading to the same final result. And because those histories are indistinguishable, their amplitudes interfere. For electrons and other half-integer spin particles, the interference has a special minus sign when particles are exchanged. This leads to the Pauli exclusion principle. Two identical electrons cannot occupy exactly the same quantum state. That rule is not a small detail. It is the reason the periodic table exists. It is the reason electrons fill shells around atoms. It is the reason chemistry has structure. It is the reason carbon behaves like carbon, oxygen behaves like oxygen, and iron behaves like iron. Without this quantum rule, matter would not organize into the rich world we know. Other particles, such as photons, follow a different rule. They can pile into the same state. That is part of why lasers are possible. So quantum mechanics does not merely make strange laboratory patterns. It decides the architecture of matter. It decides what kind of universe can exist. And this is where Einstein's discomfort becomes understandable. Quantum mechanics works with unbelievable accuracy. Its predictions match experiment again and again. It gives us transistors, lasers, semiconductors, MRI machines, atomic clocks, and modern technology. But the meaning behind it still feels strange. Einstein wanted reality to be complete and definite underneath. He believed the moon should exist whether or not anyone looks at it. He believed particles should have real properties, not merely probabilities. Quantum mechanics seem to say that some properties are not definite until the system interacts in a way that makes them definite. Einstein resisted this. He did not deny the success of the mathematics. He challenged whether the theory was complete. He believed there must be something deeper, a hidden layer, a more complete reality beneath the probabilities. This disagreement shaped one of the greatest debates in science. Einstein versus the quantum world. Order versus uncertainty. Definite reality versus probabilistic outcomes. But as experiments became more precise, nature kept siding with quantum mechanics in ways that shocked classical intuition. That does not mean every philosophical question is solved. Physicists still debate interpretation. What exactly is the wave function? What really happens during measurement? Does the wave function collapse? Do all possibilities continue in branching worlds? Is information the key? Is reality relational? There are many interpretations, but the calculation works. And physics, at its practical core, is about predicting what nature will do. Quantum mechanics tells us how to calculate. It tells us when to add amplitudes. It tells us when to add probabilities. It tells us why atoms are stable. It tells us why energy levels are discrete. It tells us why matter has structure. It tells us why observation and distinguishability matter. And this is the strange humility quantum physics forces on us. We may not be able to picture the quantum world in the same way we picture a ball rolling down a hill. But the quantum world does not owe us a picture that fits human intuition. Our intuition was built for survival at human size. Throwing stones, walking on ground, watching rivers, seeing animals move. It was not built for electrons. It was not built for photons. It was not built for probability amplitudes. So when quantum physics feels impossible, maybe that is not a failure of quantum physics. Maybe it is a sign that our everyday imagination is too small. Einstein showed us that space and time are stranger than common sense. Quantum mechanics showed us that matter and reality are stranger too. One theory bent the universe. The other dissolved certainty. Together, they tell us that the world beneath appearances is far more mysterious than the world our eyes report. And yet, from this mystery comes everything familiar. The atom, the light bulb, the computer, the chemistry of life, the stability of matter, the colors of stars, the floor beneath your feet. Quantum mechanics is not a distant theory locked inside laboratories. It is happening inside every object you touch. It is happening in every beam of light. It is happening in the atoms of your body. It is the hidden code underneath ordinary reality. So when someone says quantum physics is impossible to understand, they are partly right. It is impossible to understand if by understand we mean turning it into a tiny version of everyday life. But if we mean understanding the rules nature actually uses, then quantum mechanics is one of the greatest achievements of the human mind. It tells us, do not ask which path when the experiment does not define a path. Do not assume particles have classical properties before measurement. Do not confuse probability with ignorance. Do not expect nature to behave like a machine made of tiny billiard balls. At the deepest level, the universe is not made of common sense. It is made of rules, and those rules are quantum. Einstein may never have been fully comfortable with that, but even his resistance made quantum physics stronger because the hardest questions forced the theory to face its deepest tests. And today, we live in a world built on the strange theory he challenged. Every transistor, every laser, every digital screen, every atomic clock, every quantum sensor, all of them whisper the same message. Nature is not classical underneath. It only looks classical from far away. The double-slit experiment is not just an experiment about electrons. It is a warning that reality does not always choose the kind of story the human mind wants. Sometimes there is no single path. Sometimes possibilities interfere. Sometimes knowing destroys the pattern. Sometimes uncertainty is not ignorance, but law. And that may be the most important lesson of all. The universe is not mysterious because we are foolish. It is mysterious because it is deeper than the language our senses gave us. Einstein searched for a reality beneath the mystery. Quantum mechanics answered with a reality made of probability, uncertainty, and interference. And somewhere between Einstein's doubt and quantum theory's success, modern physics was born. So the next time you see light pass through a window, or your phone screen glow, or a shadow fall across the floor, remember this. Behind that simple moment is a quantum world where particles act like waves, possibilities interfere, atoms survive because of uncertainty, and matter holds together because nature follows rules stranger than imagination. The world looks solid, the world looks definite, the world looks simple, but underneath it is quantum. And that is why the ordinary universe is the greatest mystery of all.